Swayam Prabha. Digital India. Educated India.
Welcome back to the course Mechanics of Solids. So, in the last lecture, if you recall, so we have derived these two equations, right, by considering the equilibrium condition along x prime direction and along y prime direction. Basically, what was our objective? Our objective was to find out the state of stress in some arbitrary oriented coordinate system if we know the state of stress in x y coordinate system. Okay. So, this is the equation whatever we have obtained by exploiting or by satisfying the equilibrium condition along x prime direction, and this is the equation whatever we have got that is coming after satisfying the force equilibrium along y prime direction. Okay. So, now if you come back to this figure, so what we can establish that MP is nothing but in terms of the inclined surface, okay, mn cos theta. Similarly, your NP is nothing but mn sin theta. Okay. So, these two relations we are going to include in these two equations, okay, and these relations are coming from the geometry of the wedge. So, this wedge we have considered in the previous class, as you remember. Okay. So, now in place of MP we are putting mn cos theta, and in place of NP we are putting mn sin theta, that is coming from the geometry, simple geometry. So, if I put that, then what I will be getting from equation 1? So, from equation 1 I will be getting sigma x prime is equal to sigma x cos square theta plus sigma y sin square theta plus 2 tau xy sin theta cos theta. Okay. And from equation 2 what we will get? We will get tau x prime y prime equal to sigma y minus sigma x sin theta cos theta plus tau xy cos square theta minus sin square theta. So, these two equations I am calling as equation 3. So, what did you get? Sigma x prime in terms of known parameters, sigma x, because we started with the known parameters, that is sigma x, sigma y, tau xy and theta, because you know the orientation of the arbitrary coordinate system. So, in terms of sigma x, sigma y, tau xy and theta, you can express sigma x prime. Similarly, the tau x prime y prime can be expressed in terms of sigma x, sigma y, tau xy and theta again, right. Now, one more stress component is left out, that is sigma y prime. So, how to obtain that? So, if we consider, so if we substitute theta plus 90 degree for theta, we can obtain sigma y prime. Okay. So, in this figure if you come back, so in place of theta we are just putting theta plus 90 degree, because we are rotating the axis. So, x prime will take the position of y prime and y prime will go to the position of negative x prime. So, that is something like that. So, if you look at this figure. So, in this process basically you will be getting sigma y prime by simply putting theta plus 90 degree in place of theta, isn't it? That is simple geometry actually. So, what I am doing, I am just rotating the axis coordinate system, and I am going to find out the normal stress component sigma y prime. So, by this process I can get sigma y prime in this equation, the first equation of equation 3. If we put theta plus 90 degree in place of theta, I will be getting sigma y prime, which is equal to sigma x sin square theta plus sigma y cos square theta minus 2 tau xy sin theta cos theta. So, say this equation as equation 4. So, virtually our objective is fulfilled. That means, we have got all 3 unknown stress components like sigma x prime, sigma y prime and tau x prime y prime in terms of known stress components sigma x, sigma y and tau xy, and the orientation of the arbitrary coordinate system, that is theta. Okay. So, now basically if we know the stress components for all possible orientation of faces, right. So, if you consider a point as we considered here, that is point O, if you consider a point O, okay, and if we know the stress components for all possible orientations of faces through this point, okay, and then we can say that we know the state of stress at that particular point. If we do not know any one of the stress components, then we cannot say that we know the complete state of stress at that particular point. That means, if I know sigma x, sigma y, tau xy, okay, in case of course plane stress condition, if I know the sigma x, sigma y, tau xy all stress components at a particular point, then I will be saying I know the state of stress at that particular point, because any possible orientation of the coordinate system, if you know the orientation, that means if you know the orientation means you know the value of theta. If you know the value of theta, you can find out the other stress components, right. That is one thing. Another thing is that you should not be confused with the state of stress and the stress component. Sigma x, sigma y, tau xy, all these are stress components. Okay. Sigma x is one of the stress components, sigma y similarly is one of the stress components, and tau xy. But collectively sigma x, sigma y and tau xy, collectively that will talk about the state of stress at that particular point. So, do not get confused during this course. Okay. I mean frequently I will be telling stress component or state of stress. So, stress component means one particular stress parameter. Okay. But when I am talking about the state of stress, that means I know all the parameters, all the stress components at that particular point. Okay. So, now with that, whatever we have got from equation 3 and equation 4, from there we are going to establish some important and very handy and helpful graphical representation of the state of stress, and that is known as Mohrs circle representation. So, that was proposed by scientist Mohr, and that is found very handy and very helpful actually in the analysis of your state of stress. Okay, without going through the rigorous analysis or rigorous calculations, like rigorous mathematical calculations, you can very simply get the state of stress on any arbitrary coordinate system. Okay. So, let us establish that graphical representation and let us get the advantage, or let us understand the advantage of that particular graphical representation of the Mohrs circle. Okay. So, Mohrs circle representation of plane stress. Okay. Now, if you look at equation 3 and equation 4 once again, you can simplify this equation by using your trigonometric formulation, okay, and you will get the equations like that: sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. Okay. Similarly, tau x prime y prime is given by minus sigma x minus sigma y by 2 sin 2 theta plus tau xy cos 2 theta, and you will be getting sigma y prime equal to sigma x plus sigma y by 2 minus sigma x minus sigma y by 2 cos 2 theta minus tau xy sin 2 theta, equation 5 say. I am not doing anything new. So, previously derived equation 3 and equation 4 if you consider, and if you do little bit simplification, okay, based on your trigonometric formulation and other things, algebraic formulation, you will be getting these 3 equations. They are the revised version of your equation 3 and equation 4. Okay. Well, so now if you look at equations, the first equation of equation 5, so that means this one, that is the expression of sigma x prime in terms of sigma x, sigma y, tau xy and theta. Okay. So now what I am doing? I am doing some graphical construction. I am choosing one coordinate system. Along x axis we are putting the normal stress, along y axis we are putting the shear stress. Okay. Some graphical representation or graphical say construction we are performing. Okay. So, in that graphical construction, if you look at the first equation of equation 5, I am just taking the first component of equation of this first equation, the sigma x plus sigma y by 2, and that I am plotting here. Say that is say considered, say this is the point. Okay. So, point, so that point is say I am calling as C. Okay. So, C point is giving me this first component of the equation. Then what I am doing? I am drawing one line in such a way that is making an angle twice theta, okay, with the sigma axis, and this is basically CB and CD I am calling, where CB equal to CD equal to sigma x minus sigma y by 2. I can do that because I am doing the graphical construction. Okay. So, now again what I am doing, I am just drawing one normal. I am drawing one normal perpendicular line on CB, and similarly I am drawing another perpendicular line on CD. Okay. So, I am drawing one perpendicular line on CB, another perpendicular line on CD in such a way that this say BA I am calling, and this is I am calling say DE, okay. So that this BA is equal to DE is equal to tau xy, because these are all known terms, sigma x, sigma y, tau xy. So, you can play with those terms, right. So, what I have done once again, I have taken a coordinate system, okay, space in sigma tau space, okay. In that space I am choosing one point C in such a way that C point, the abscissa of C point is sigma x plus sigma y by 2, that is the first term of this equation. And then I am drawing one line say DCB in such a way that is making an angle twice theta, okay, with the sigma axis. And then I am drawing two normals BA and DE in such a way that BA equal to DE equal to tau xy. I can do that, right. So, let us come back to this figure. If you look at this figure on the slide, so that construction is here. So, this is your B point, C point, okay. This is your B, this is your A, D and E, whatever construction we have done. So, that construction is shown in the figure, okay. So, now what I am going to do, let us write down that while laying out sigma x prime say along the sigma axis, the first term. So, what I am getting? So, I am considering this equation only, okay. So, I am just, so sigma x prime I am just trying to plot on sigma axis. So, sigma axis is nothing but a normal stress axis, okay. So, I am trying to lay out sigma x prime along the x axis. The first term, that means this is the term, okay, on the right of the equation for sigma x prime is represented by OC. If you look at the figure, you will get it. So, first I plotted the point C in such a way that OC, O is the origin. So, OC is nothing but your sigma x plus sigma y by 2, right. I constructed the graphical representation in such a way that OC is nothing but the first term. Now, the second term now what is the second term? Now, if you look at CB here, okay, this is CB. Now, what is the meaning of the second term? So, CB is nothing but sigma x minus sigma y by 2, that is given, and in that way we have constructed the representation, graphical representation, right. So, sigma x minus sigma y by 2 cos 2 theta is nothing but the horizontal component of CB on the sigma axis, agreed or not. So, that second term is represented by the horizontal component of CB, agreed. And so, this term we have got the meaning or representation of the second term. Okay. Now, if we consider the third term, that means this term, the third term is represented by the horizontal component of BA. Agreed? So, if you look at this figure, so basically first you have got up to this is your first term, then you have got up to this is your second term, that is the horizontal component of CB, and the third term is the horizontal component of BA, that means up to this part. Okay. This is your first term, this is your second term, this is your third term. Agreed? Now, if you have got this, now the abscissa of point A is nothing but the sigma x prime. Agreed? The abscissa of point A is nothing but the sigma x prime. So, what we can write from this, the normal stress sigma x prime is thus represented by the abscissa of point A. Very, very important. Okay. Similarly, if you look at this equation, the second equation, okay. If you look at the second equation, we will be getting the ordinate of point A will be giving me tau x prime y prime. So, anyway, so that we will be taking in the next class. So, just you think about this equation, the first term of this equation and the second term of this equation, again it will be coming from the graphical representation, and that will be represented by the ordinate, okay, the y axis of the A point. Okay. So, we will take that thing in the next class. So, I will stop here today. Thank you very much.